Hello everybody, and welcome to another video on my channel. Today we will be talking about double derivatives, which are basically second derivatives where you take the derivative of the derivative. So without further ado, let's move on to the actual lesson. What is a double derivative? Basically, it's the derivative of the first derivative, so it's the derivative of the derivative. The notation is f double dash of x, or d squared f over dx squared. And then and another way to write it is if y is equal to f of x, then y double dash or d squared y by dx squared. Basically, it's the rate of change of the rate of change. The geometric interpretation is the concavity of the curve. F double dash of x is equal to 0 is concave up, where the curve bends upward, and f double dash x is less than 0 is concave down, where the curve bends downward. It's a little more complicated than that, but we won't be covering concavity much. That will be in a later video. But what we should probably know is the physical interpretation of this. Basically, it's the acceleration of, if f of x represents position, it's the acceleration of that object, where f dash of x, this first derivative of x, is velocity. Now, there are two different methods to figure out the limit definition of the second derivative. The first method is to use f double dash x is equal to limit as h approaches 0 of f dash x plus h minus f dash of x divided by h. Keep in mind that the first derivative limit definition is f of x plus h, not f dash, so that's the difference. And the second method is limit as h approaches 0 of f of x plus h minus 2f of x plus f of x minus h, all divided by x squared. So again, it's the rate of change of the first derivative, or more accurately, the limit of the rate of change. Let's move on to our examples. We have three main examples for today, so let's get started. The first example is to find the second derivative of f of x is equal to 4x to the power of 5th minus 3x cubed plus 2x minus 7. So what happens is that first we need to figure out the first derivative. So f dash of x is equal to, using the power rule, we get 20 x to the power of 4 minus 9 x squared plus 2. And then minus 7, since it's a constant, it will not be counted, and its derivative is 0. Then we have to take the derivative of f dash of x to get f double dash of x. So f double dash of x is equal to, if we take the power rule, x to the fourth derivative is 4x cubed, so times 20 is 80x cubed, 18x, and then plus 2 will just get canceled out, and it'll become 0. So there you have it, the derivative of the second derivative of 4x to the power of 5 minus 3x cubed plus 2x minus 7. And here's the solution, where the first step is to find the first derivative, and the second step is to find the second derivative. This will pretty much be how most of our problems go. First we find the first derivative, then we find the second derivative. Now our next example is to find the second derivative of g of x is equal to e to the power of x plus ln x plus sine x. So if you don't know the derivatives of e to the x and ln x, for e to the x, it's just e to the x, and for ln x, it's 1 by x. That was covered in my last video, where I also proved that in the general form of the logarithmic and exponential functions. So please make sure to check that out. Now, what we have to do is, first we have to find the first derivative before we can find the second derivative. As I said in the last example, that's pretty much going to be the standard path. So let's go step by step. The first derivative of e to the x is e to the x. then plus 1 by x for the derivative of the natural logarithm of x, then plus cosine of x. Now g double dash x is the derivative of g dash of x. So again, we'll get e to the power of x. Then, using the power rule, we'll get negative 1 by x squared for the derivative of 1 by x. Because the derivative of 1 by x, you can call it x to the power of negative 1. Then using the power rule, you'll get negative 1 times x to the power of negative 1 minus 1. So negative 1 times x to the power of negative 2 is negative 1 by x squared. Then the derivative of cosine of x is negative sine of x. So there you have it again. The second derivative of g to the x is equal to e to the x plus ln x plus sine of x. And here's the solution again. Again, following a very similar framework, just find the first derivative and then find the second derivative. Now, as we get better and better, especially like functions with like e to the x or sine of x, because we'll be able to like memorize that and kind of recognize the patterns. Like the first derivative of sine x is cosine of x, then negative sine of x, then negative cosine of x, then sine of x. It kind of loops every 4. If you know that, you can start calculating pretty much every derivative for sine of x, and understanding how that works with cosine of x would also be very helpful. Then also e to the x, the natural logarithm of x, and pretty much all functions related to the power rule can also be evaluated like that. So it starts to become faster and faster, so you won't have to exactly work through every step. But it's a good idea to do it because, let's say you get the answer wrong, you'll know where you got it wrong and you can redo it, because the best way of learning is by doing. Then the final problem for today is to find the second derivative of h of x is equal to 3x plus 1, to all to the power of 4. Now, the first thing we need to do is find the first derivative. The plan is pretty simple. First, we have to identify that the h of x is equal to 3x plus 1 to the power of 4 needs to be differentiated by the chain rule. So the outer function is u to the power of 4th, and the inner function is 3x plus 1. So differentiating the outer function, we get 4u cubed, but u is 3x plus 1, so we get 4 times 3x plus 1 cubed. Then we get multiplied by the derivative of 3x plus 1, which is equal to 3. So that in the end becomes 12 times 3x plus 1 cubed as the first derivative. Now the second derivative follows a very similar structure where we can remove 12 from the equation, and 3x plus 1 to the power of 3, that'll become 3 times 3x plus 1 to the power of 2. Then 3x plus 1 derivative is again 3, so that'll be 3 times 12, or 12 times 9, which is, if I'm correct, 108 multiplied by 3x plus 1 cubed. Sorry, squared, not cubed. So that's pretty much the process for the final problem, except it was just slightly more complicated using the chain rule instead of just our basic power, exponential, logarithmic, and trigonometric function rules. Now, this is probably the point where things start to go from relatively long to it can take a long time to solve these problems, because let's say I tell you to find the double derivative of something in the chain rule plus the quotient rule and the product rule all stuffed within each other. Then I layer on top trigonometric functions which require the chain rule as of itself. Let's say I have tangent of x, then that becomes secant squared of x. Then you have to use the chain rule again you have to use the chain rule to differentiate secant squared of x. So it starts to get very complicated, and it'll get even more complicated as we start to include implicit differentiation, basically a way of differentiating functions of y. But that's not needed for now, so let's move to the solution. And over here, it says find h dash of x using the chain rule, which is what we did. Then we find the second derivative again using the chain rule. So it starts to get more complicated when we start using the chain rule, because it'll just be more algebra. Technically, it's not more complicated, but it's just more algebra and more places to make mistakes. Here is what I call concavity and inflection points. It's what you call it in math. This is pretty much an application of second derivatives. We could cover it right now, but it'll normally be covered in future videos where we actually explore more applications of derivatives like related rates, optimization, etc., where it requires knowledge of concavity and inflection. So concave up is again where we have the second derivative of x is greater than 0. Then concave down is f double dash of x is less than 0. Inflection point is where f double dash of x is equal to 0, and the concavity changes from down to up or up to down. Then, to find these points of inflection, find where f double dash of x is equal to 0, then check sign changes. This will be covered more later in the calculus series when we talk about applications, but for now, this is pretty much all you really need to know. Now, before we leave, I'd like to give you a few practice problems. The first is to find f double dash of x for f of x is equal to 2x to the power of 6 minus 4x to the power of 4 plus x squared minus 5. The second one is to find the second derivative of g of x is equal to x squared times e to the power of x. And hence, you're going to need to use the product rule and not just your basic other rules. And the third one is in fact slightly unique. I debated whether to add this or not since I didn't cover it in my examples, but in the end I chose to because I talked about the limit definition earlier and how you can substitute, and it doesn't really use anything I haven't shown you. So first you have to use the limit definition, which is all the way above. You can go back in this video and find the limit definition for the second derivative of a function to find it for f of x is equal to x squared plus 2x. And thank you so much for watching this video. I'm really happy you're here. You watched to the end. And if you did and you found my content educational and you enjoyed it, please make sure to like, subscribe, and hit that notification button for more awesome videos just like this. And, of course, only do that if you like my videos and find them educational. Then, number 2, please make sure to comment down below any suggestions, tips, or anything for the channel, because it'll be really happy if you do, and I'll be able to improve my channel for all of you people watching this video. So, thank you so much, see you in the next one, and bye-bye.